2024, part 17. This is a paper discussion about robots application. The paper Quest Self-Supervised Skill Abstractions for Learning Continuous Control by Garg et al. From Georgia Tech. The paper's in the show notes and the link. The idea here is really interesting. The reason we picked this paper to discuss is a couple of things. The big picture, for people who are new to this podcast, just real bit quick, we talk about scientific papers a lot in this podcast. This is not a science podcast, and this is certainly not a paper critique discussion type thing. So if you want more detailed technical discussions, this is not the forum. The purpose of this podcast is to give people a sense for what it feels like to run a hedge fund. We are actually we are an active hedge fund, and we're invested in fundamentally new concepts and engineering practices. In other words, we invest in technology, and particularly we're interested in robotics. So what we do is we read a lot of scientific papers that are related to robotics because we want to understand where the science is, and where we actually end up investing is where where science, technology, and entrepreneurship overlap. What do we mean with that? Well, if you think about it, like there's an exploration space which we call science, which is the form of inquiry. The scientific method allows us to tap in the dark and see what's out there. We don't know what's possible. We try. That's what most academics do, at least the good ones. And this is the purpose of this particular discussion. The purpose of following Neurips or other conferences like that, in particular CVPR. That's the purpose. Like, what's out there? Sometimes the science is useful. Sometimes it's interesting. Sometimes it's inspiring. Sometimes it's not. This is definitely a paper that I would call useful, maybe not as inspiring as others, but definitely useful. And what the authors are doing here is discretizing actions. So you have an action, which is the robot goes, let's say, if it's a robot on wheels, it drives towards a bottle, grabs the bottle and brings it back and puts it on the table. That is a continuous motion, action, sequence, and that can be discretized. And that's what the authors are doing. They're discretizing this, and they're learning these discrete actions and transforming them into what's called the codebook, which is, in simple terms, the idea is to split a continuous motion action into discrete motions and actions. Let's call them tokens. So motion action tokens. In other words, turn the action into motion tokens, and then use a GPT-style transformer to learn with self-attention, very similar to what happens with text, and try to predict, given a prompt, what the robot should do. The idea fundamentally is to have a zero-shot learning capability for a robot. The same way when I put a prompt in Grok 3, I get a pretty good answer in zero shot. I don't have to train the model, fine-tune the model. I can, chain of thought the model. I can use reasoning and deep reasoning and things like that, which help me with the train of thought. But the model itself, I'm not changing the model. I'm not changing the weights or any of that. So that's the goal here, to have a pre-trained model that has the knowledge of what it means to act in space, in three-dimensional space, actually four-dimensional space, including time also. So it has this latent representation of what it means to move and act in space, and then use that knowledge to prompt new actions in test time that the robot hasn't seen, or maybe has seen, but slightly different, and it can act. The idea here is to generalize the robot learning experience. So we don't have a robot which is if we take the spectrum of robotics, right, we go from what's actually out there in the factories right now, the KUKA robots, the Fanuc robots, and then we go all the way to the other side. Let's call that the Optimus, the Tesla Optimus robot, or at least the goal of the Tesla Optimus robot. The spectrum is from determined, rigid, repetitive actions, which is KUKA, towards completely flexible, learning while doing, acting in the environment, and adjusting to changes in the environment. So that's the spectrum. Right now, we are trying to build systems, let's call them humanoid robots, which is a robotic system that is fully flexible in the ability to adapt to the environment, and that can also learn from those actions. And what the authors are trying to do here is build an architecture that allows for that to happen at scale in a structured way. So they're building a code book. The steps are the following. You have cameras which see what the robot is doing, and you train the robot on actions, and then you translate what the robot sees combined with its actuator information. So at this point, I see this and my actuators are that. At this point, I see this, my actuators are that. So this sequence is then translated into a code book, or let's call it like a scrapbook, which says, when you saw this, this is what your arms did, and I'm going to call this the reach skill, and I'm call this the turn skill, and I'm going to call this the grasp skill. So you're going to turn these millions and millions of pixel information combined with millions and millions of actuator information into more manageable skill information. And that's the code book. During training, by the way, the robot is very deterministic. So it's either teleoperated or it has a deterministic script. So there's no adaptation or anything. The robot is actually just doing that, grasping the bottle, let's say teleoperated, right? So, or behavioral cloning or things like that could be used for training. Once it's done that, you now have this code book trained. So you've trained the robot on many different actions. You've created the code book, and now in test time, you're using new actions and matching them to code book and learning from these new actions how to match to the code book. So finally, at inference, when you expose the robot to the wild, it can see something and say, okay, I remember in my scrapbook when I see this, I should be doing that. And because it's discretized and trained on a GPT-style next token prediction model, it should be able to auto-complete a task given a prompt, whether that prompt is textual or you can show it, or that's not so clear to me, but that doesn't really matter. Let's say you have a textual prompt. You tell the robot, hey, go fetch me this bottle. The robot can auto-complete the task the same way that if you prompt something in GPT, it can auto-complete the text. So this paper is highly influenced by the recent developments in transformer technology. It's an attempt to build a foundation model for robotics. I think they don't call it like that. It's a very technical paper, but I think it's an interesting approach. And once you sort of peel the onions a little bit here, you really start to understand the power of the transformer technology and how it can be used in four-dimensional space against 3 dimension plus time. So to summarize, this paper is an attempt to discretize motions, to create a code book with discretized motions that have added semantic meaning. So instead of just a vector, there is more meaning to a certain skill, let's say reach, and then that skill reach can be used in different contexts, right? It can be reached if you reach a bottle, but it can also be if you reach a glass or if you reach an apple. And turning your hand can be used for many different types of of use cases. So that's the idea. That's the generalization here, which I think is really interesting. I like the idea of the codebook. I like the idea of discretization. I like the idea of quantization, which is just means that you kind of round those vectors that define the skills. So you have maybe a vector that corresponds to reach, and then another vector which is a little bit different that has a similar reach, and you can just quantize this because reach is reach. And then I guess one of the things that the authors are mentioning, or sort of on the discussion side, is that the robots were tested on very similar tasks. So they weren't let out in the wild yet. If you train a robot in a kitchen picking up stuff, you can't just put it in a factory and let it, do stuff with tools. Like that transition seems not to be fully solved. The embodiment problem, as usual in robotics, has to be solved. So those, I believe, are the two main drawbacks. But again, I think an interesting approach. And why is this relevant? Just to finish this episode, it's relevant because we believe that Optimus as a humanoid robot has a lot of potential. We believe that the Tesla FSD is a good base for transfer learning onto Optimus, but we also believe that it's just the beginning, and that maybe a quantization of skills based on what FSD has learned in driving could be an approach that they're using. It's not clear what Tesla actually is using, but what we're trying to do here as investors is try to understand what they could be using or what's out there, and then hopefully calibrate this with information that we get from the company. Thank you.